Flow meters are indispensable for applications like process control or fluid dispensing. There are lots of different technologies available for a flow meter, and we're going to look at two of them. Well, two basic technologies. One is positive displacement flow meters. So here are three examples. First, we have a lobed impeller, which is a very durable but slightly less accurate type of meter, and the rotation of these shafts is a direct indicator of the flow through the meter, because if no fluid can go between the lobes or between the lobe and the wall, then every rotation of the shaft has the same amount of fluid going through it. Another technology is Rotary Vane, which is more precise but less durable, and here's a video demonstrating the technology for a Rotary Vane flow meter. And I'll let you watch it. I'll give you a minute to watch it and then come back to this video. So here's the video number, and you just pause this one and then go ahead and watch this, and then come back to this video. So go ahead and I'll wait until you've watched that. So now I'm assuming you've come back to watch it and you found your place. Another technology is the nutating disc. Here the fluid flow causes this disc to wobble. So here's the inlet port and the outlet port, and the wobbling disc causes a rotation of the shaft. So again, it's the same technology, that the fluid flow causes rotations that can be measured by an angular displacement sensor. And here's a video demonstrating that. So the flow through the green ports will cause this rotation of the shaft. Now there's slightly different implementations, but the concept is the same for all these positive displacement flow meters. The second method of measuring flow is magnetic flow meters, and that's based on the principle that a conductor moving through a magnetic field will experience an induced voltage. So here our conductor is the fluid, and the induced voltage is given by this equation. B is the strength of the magnetic field, L is the length of the conductor, and U is the speed of the conductor. So the length L is proportional to the tube diameter. And for fluids that are not good conductors, this voltage is going to be small, and so it requires amplification. Now, one thing that bears consideration is how to obtain mass flow rate from a flow meter, especially for compressible fluids. Here's an example of finding the mass flow rate of gas using a flow meter. We're given that nitrogen at 50 degrees C and 3/4 of an atmosphere is determined to have a flow rate of 26.2 cubic meters per minute with this positive displacement flow meter. And that measurement has an uncertainty of 0.15 cubic meters per minute. So we want to find the mass flow rate and the uncertainty in that mass flow rate. So if a company is selling nitrogen, they need to know how much to charge the customer for. And so they need to know the mass that was delivered. The equation for mass flow rate in terms of volumetric flow rate is density times the volumetric flow rate, Q. And density for an ideal gas is P divided by R times T. And R is different for every gas, and it can be determined from the universal gas constant divided by the molecular weight, M. Now, combining all these, we get that the mass flow rate is P times M times Q divided by universal gas constant times temperature. So we have R times temperature in the denominator here. Now, plugging in all the values that we're given, we end up with mass flow rate of 0.0208 grams meters cubed per minute centimeters cubed, and just multiply by 100 cubed to get rid of the centimeters and meters cubed, and we end up with 2,700 or 20,764 grams per minute, and I mistakenly put 20.8 kilograms per minute, but it should be 20.8. So let me go ahead and fix that. Now that that mistake is corrected, we have that the mass flow rate is 20.8 kilograms per minute. And up here we have the pressure was 0.75 atmospheres, and the molecular weight is 28.02, and that's in units of grams per mole. Q is 26.2 meters cubed per minute. Ideal gas constant is 82.057, and that's units of centimeters cubed, atmospheres per degrees Kelvin times mole. And finally, the temperature is 50 degrees C, and then that's 323.15 degrees Kelvin. Now the uncertainty is just, we only have one measurement with uncertainty, and that's the flow rate, volumetric flow rate. And so the uncertainty in our result is given by this equation. It's the product of the measurement uncertainty and the partial derivative of the result with respect to that one measurement. So partial of m dot with respect to q. That works out to be what's shown here. And so the final value for that is 0.189 kilograms per minute, which is about 1/2 of 1% of the result of the mass flow rate.